Hello, tensor friends. The last time we had a lot of fun looking at the Gaussian curvature of a paraboloid. This equation here, z equals x squared plus y squared. And we'd parameterize that with u and v. So we said x equal u, y equal v, so z equal u squared plus v squared. Well, this time I want to parameterize that with the angle theta and the radius of a circle. So this is just a bunch of circles, right, all stacked up together, and the radius increases as you go. So we know that a circle in here, from using the coordinates that we parameterize that as x equal r sine theta and y equal r x equal r cosine theta and y equals r sine theta. So we would put that in here and square it to get z. So that's what we're going to do here. So having done that, we can define a point on this manifold like this, right? So this point now is a function of r, the radius of the circle, so it goes up or down, and the angle around that circle, whichever circle that we pick. Okay, and the point of doing this is that now we can define some basis vectors right on the manifold. Okay, now these basis vectors are in a tangent plane at that point. Now, you saw when we did the first video, I'll leave a link in the description, that in order to find the Gaussian, the curvature, we had to find what's called the normal. So I just crossed these two basis vectors to find this normal. Now look at this. This normal is sticking out away from this manifold into this, which is called the ambient space. So this is a manifold embedded in the ambient space. Okay, that's the way Gauss did this in order to find how things move on a curve. Well, Gauss had a Padawan learner named Bernard Riemann, and when it was time for him to do his dissertation, he said, "Wait a minute, master, do we really need this reference to an ambient space in order to study what's going on the surface?" And of course the answer is no, you don't. So basically he developed Riemannian geometry, which is intrinsically studying the surface of this without any reference to the ambient space. And that's what we're going to do. Okay, so now we're going to calculate the Riemann, the curvature of that paraboloid. Did I spell that right? I think so. So we already said we parameterize the surface like this, right? In the last video, we found our surface basis vectors like this. So we defined this vector that would be on that tangent plane that we just looked at. Here would be the basis of vectors in u and v. We found the tensor, so this is eu.eu, eu.ev, ev.eu, and ev.ev. Now comes the hard part. We need to calculate all this stuff. The inverse metric tensor, Christoffel symbols, Riemann tensor, Ricci scalar. This is a lot of work. Let me show you something absolutely amazing. This well-coiffed, handsome lad has designed an online calculator, ChristoffelSymbolsCalculator.com. It is so good. I can't believe it. And it's free. He would like for you to donate. I encourage you to if you use this, but it's so nice. That's a lot of work. So you define your two parameters. We got u and v. You type in your metric, the tensor, which we hid. So we had 1 plus 4u squared, 4uv, 1 plus 4v squared. You type that in, and so he shows you what your metric tensor is. And then you go here and you choose what you want. So I wanted Christoffel symbols of the second kind, a Riemann tensor of the second kind. That's where you have an index in the covariant position. The Ricci tensor and the Ricci the scalar. And you hit calculate, and look what you get. Does the Christoffel symbols, does the Riemann tensor. Do you know how much work this saves? My God. I just love this kid. Look at this. There's your Ricci tensor, and finally the Ricci scalar. This is what we were after. So, if you want to use this, I highly encourage you to support this young man because this was an excellent thing he did. Okay, so here's what we were after. The Ricci, the scalar, is given as this, parameterized in U and V. And in the first video, we calculated the Gaussian curvature, which was 4 over the same denominator. So, of the few of these, the surface parameterization, the studies I've done, it turns out that the Ricci scalar is always 2 times the Gaussian, the curvature. Is that true for all surfaces? I don't know. I've only done a few, but it turns out that it was. So anyway, wasn't that fun? And I'm so glad I found that online, the calculator. I'll see you later.